Hi, my name is Rachel Ka-Ying Tsui. I'll be presenting this project in collaboration with Ana Maria Gonzalez-Barrero, Esther Schott, and Krista Byers-Heinlein. This project aimed to better understand the nature of translation equivalent learning in bilingual infant vocabulary development. To look at this, we came up with a quantitative model. Children growing up in bilingual environment are exposed to two languages and have to learn two different labels for the same concept. For example, to refer to the same red-skinned fruit, an English-French bilingual child must learn the word apple for English and the word palm for French. These cross-language synonyms are known as translation equivalents. But it actually involves a two-step process to establish a translation equivalent. The first step is to learn a first label for a concept. Here, we call these singlets. For example, an English-French bilingual child first learned the singlet apple. Then eventually, they will learn its French translation equivalent palm. It has been assumed that the first label and the second label are learned differently because translation equivalents are thought to hold a special status in bilinguals' developing lexicon. Especially the strong semantic overlap, it's assumed to cast an effect on vocabulary acquisition. Previous literature has laid out three competing accounts with respect to how bilingual children learn translation equivalents. Early theory claims that translation equivalents are missing from bilingual children's early vocabularies. As young bilinguals do not differentiate their languages, word learning biases such as mutual exclusivity leads them to assume that a reference is only associated with one word. Therefore, bilingual children reject translation equivalents in favor of learning one label for each reference. We refer to this as the avoidance account. More recent literature proposed that the semantic overlap facilitates translation equivalent learning. For example, when an English-French bilingual child encounters the word palm after having learned apple, part of the word learning task is already accomplished, so it's easier to attach a second label. Therefore, bilingual children favor learning translation equivalents. We call this the preference account. The two previous accounts assume that translation equivalents are special and vocabulary learning in bilinguals is different from monolinguals. However, some studies have suggested that bilingual children's two languages develop relatively independently, and language learning tend to be tightly correlated within a language, but not across languages. With this, it is predicted that bilingual children may learn translation equivalents and singlets in a similar way. Here, we refer to this as the neutral account. Our study will try to test these three accounts, but before we turn to the specifics of our study, there are some details that we need to go through. Considering translation equivalent learning, there are some contributing factors that are often not taken into consideration in previous studies. Here, we will specifically look at vocabulary size in each language. Since translation equivalents are the overlaps between two languages, the number of translation equivalents will, in theory, be constrained by the number of words a bilingual knows in each language. For example, for a child who knows a similar number of words in each language, there will be more potential for some of those words to overlap, leading to a higher number of potential translation equivalents to be learned. In contrast, if a child has a less balanced vocabulary across the two languages and know a lot less words in their non-dominant language, regardless of how many words they know in their dominant language, the maximum number of translation equivalents they could learn would be limited by the number of non-dominant vocabulary they know. Moreover, there is a limit on how many words a child could learn. This relates to another factor, which is the learnability of words over time based on a child's developmental level. Evidence from monolingual children shows that due to cognitive and linguistic biases, some types of words are characteristically learned before others. For example, across many languages, including English, children show a noun bias in their early lexicons, while other classes of words, like prepositions, are rarely known at the onset of lexical development. So imagine a baby who is 18 months old versus a baby who is 30 months old. There will be many more possible words for the older babies to learn compared to the younger one. So how do we know the number of learnable vocabulary? If vocabulary is measured with an instrument such as the CDIs, a reasonable option is to estimate how many CDI words are learnable at the 90th percentile given the child's age. For example, for an 18-month-old English-French bilingual infant, the number of learnable vocabulary would be roughly 250 words, whereas a 30-month-old could learn about 650 words. Taking into account the contributions of vocabulary sizes and developmental level, our study asked what the nature of translation equivalent learning is in bilingual children. In particular, we aim to test the 3 accounts of translation equivalent learning. Each account would lead to different outcomes. Under the avoidance account, translation equivalents should be harder to learn than singlets. Under the preference account, translation equivalents should be easier to learn than singlets. Under the neutral account, translation equivalents are similar to learn as singlets. Here we present the bilingual vocabulary model. This is a novel approach that models translation equivalent knowledge as a function of bilinguals' own vocabulary size in each language, given a child's developmental level. First of all, we define language dominance based on vocabulary size. Dominant language would be the language in which a child produces a greater number of words, whereas non-dominant language would be the one in which a child produces a fewer number of words. Under this model, learning a translation equivalent pair can be described as the joint probability of learning each of the words in the pair. The logic is similar to that of the probability test for independence, where the independence of 2 events is tested as the probability of their intersection computed by multiplying the probability of each individual event. So probability of event A times probability of event B. In this case, we can reframe the probability of intersection as the probability of words known in both languages, and replace event A and event B with words known in the dominant language and words known in the non-dominant language. Let's walk through this in details. Probability of dominant words known would be the number of dominant words a child knows divided by the total number of possible learnable words. Likewise, probability of non-dominant words known would be the number of non-dominant words a child knows divided by the total number of possible learnable words. Take the case of a 21-month-old child as an example. According to the 90th percentile on the CDI, the number of learnable vocabulary would be roughly 400 words. And if this child knows 300 dominant words, then the probability of dominant words known would be 300 over 400. Similarly, if this child knows 100 non-dominant words, then the probability of non-dominant words known would be 100 over 400. With these 2 probabilities, we can then compute the expected outcome of words overlapping between the 2 languages. In other words, the expected number of translation equivalents. Following tests of probabilities, the expected number can be calculated by multiplying the probability of intersection between the dominant and non-dominant language by the number of potential learnable vocabulary. We can then simplify the formula as follows. In brief, the expected number of translation equivalents can be calculated by the number of dominant vocabulary times the number of non-dominant vocabulary divided by the number of learnable vocabulary. In this example, it gives us a total of 75 translation equivalents. So far, what we have gone through are all based on the idea that translation equivalents are learned independently, which corresponds to the neutral account. We further introduce a bias parameter, which allows us to examine which of the three accounts better captures the pattern of translation equivalent learning. For the neutral account, bias is exactly 1, meaning translation equivalents are neither harder nor easier to learn than singlets. For the avoidance account, bias will be less than 1, meaning that translation equivalents are less easily learned than singlets. For the preference account, bias will be greater than 1, meaning that translation equivalents are more easily learned than singlets. We will now validate our model. First, we will look at some simulations under the neutral account and compare them to real-life observed data. Then we will test the bias parameter in the model and see which account fits the observed data better. To run the simulations, we generated data for 216 simulated children using a whole range of possible dominant and non-dominant vocabulary sizes. These data will then be compared to some real-life observed data, which were archival CDI data collected from 200 English, French, 18 to 33-month-old bilingual children from Montreal, Quebec, Canada. There are a total of 611 translation equivalents across the English and French CDI forms. Let's look at the pattern of translation equivalent learning predicted by the simulation. First, we'll look at the relation among translation equivalents and other vocabulary measures at different levels of vocabulary balance. Vocabulary balance is based on the proportion of words produced in the non-dominant language relative to the total vocabulary produced. For example, for a child who knows 55 English words and 45 French words, English would be the dominant language and their vocabulary balance would come out at 0.45, meaning that they are highly balanced between the two languages. On the y-axis, we have the total number of translation equivalents. And in this panel, the x-axis represents the total number of vocabulary produced with dominant and non-dominant vocabulary combined. Here, looking at the red line, those stimulated children with more balanced vocabularies will produce more translation equivalents. Moreover, as the number of total vocabulary increases, translation equivalents also increase. We observe the same pattern with dominant vocabulary size, where stimulated children who produce more dominant vocabulary will produce more translation equivalents, and those with a more balanced vocabulary will also produce more translation equivalents. Finally, the simulation shows that different from total vocabulary and dominant vocabulary, non-dominant vocabulary size does not interact with vocabulary balance, and it's an almost perfect predictor of translation equivalent knowledge. When we compare the model simulations with the pattern in the observed data, so here in the bottom panel, we see a strong correspondence between the two. This suggests that the model's predictions are confirmed in the real-life observed data, therefore validating our model's approach. Now we'll look at the bias parameter in the model and see which account fits real-life observed data better. We predict the observed number of translation equivalents we obtained from the 200 infants using the earlier formula from the bilingual vocabulary model. Specifically, we test how the number of translation equivalents observed in each individual child could be predicted using the child's own vocabulary size in each language. We built a linear regression model to test this. We forced the intercept of the linear regression model to 0, since no translation equivalents are expected to be produced if a child does not know any dominant or non-dominant vocabulary. Then we allow the model to return the bias parameter with the regression coefficient estimated by the model. This would indicate what the bias parameter needs to be in order to fit how many translation equivalents we observed in the data. The linear regression model estimates a bias coefficient of 1.02, which is extremely close to 1. Also here, we plot the observed and predicted number of translation equivalents against each other. The black diagonal dashed line represents a case where the bias parameter equals 1, such that the predicted and observed number of translation equivalents are equal. And the solid blue line representing the model prediction is very close to the dashed line. These show that overall, the neutral account fits the data really well, suggesting that translation equivalents are neither harder nor easier to learn than singlets. Well, it looks like the story may end here, but there are some additional findings that we want to share with you. A closer examination actually shows that the slope for younger children with smaller vocabulary size is steeper. And the bias parameter suggests that translation equivalents are more easily learned. Whereas the bias parameter for older infants with larger vocabulary size is still close to 1. These suggest that there may be a qualitative change in translation equivalent learning from the preference account to the neutral account as bilingual infants develop and learn more words. We can't quite explain why these qualitative shifts happen, and if you have any insight, we would love to hear that. And we look forward to having a discussion at the Q&A. Overall, our data closely aligned with the neutral account. We show that translation equivalents are actually not special and are learned in a way similar to how singlets are learned. They are contingent upon a child's vocabulary size in each language and their developmental level. This result is consistent with previous studies, which suggest that vocabulary in each language develops independently. With this, singlets and translation equivalents are equally learnable. And perhaps translation equivalents are learned because they are the by chance lexical overlaps shared between bilinguals' two lexicons. The bilingual vocabulary model represents a novel theoretical and methodological advance which predicts bilingual vocabulary development as a function of child-specific word learning experience. The inclusion of quantitative factors, especially children's own vocabulary sizes, together with their developmental level, it's a unique aspect of our integrated approach. It will be interesting for future studies to take into consideration other factors, such as a child's efficacy of word processing and other qualitative factors, including quality of input and SES, to better characterize bilingual vocabulary development as a function of experience. Moreover, our model presents a simplified computation, assuming that children encounter the same words in each of their languages and therefore are exposed to equal word learning opportunities. Cross-linguistic data has provided evidence of a high degree of commonality in the first words children produced. For example, words for important people, social routines, and common nouns are among the first words children acquired across languages and cultures. It is therefore reasonable for our model to expect that bilingual children would be exposed to a similar set of reference and labels in each of their languages. However, future study may look into the possibility of how having different linguistic experience in each language would affect translation equivalent learning. To sum up, our bilingual vocabulary model proposed that translation equivalents do not hold special status in early bilingual vocabulary development, but they are actually learned through child-specific word learning experience. Thank you so much for listening. If you are interested in knowing more about this project, here is the QR code to the preprint. And we will love your comments or feedback on this study. We look forward to seeing you at the Q&A section. Thank you.